welcome to my talk. I'm Patricio Whittingslow. Thanks for the presentation, introduction, Eric and Angelica. So, let's start with some curiosities about me. I work at a startup called Aerospace in Buenos Aires, Argentina. I studied mechanical engineering. That might come as a surprise to some of you. I also teach an undergrad course in programming with Python. And I started using Go for hobby in April 2019. And it's been a little under 2 years using Go professionally. One of my favorite topics is simulation. So anything from rigid body dynamics to material phenomena. So finite element method and other stuff. This talk will follow Aerospace Go. We'll follow the history of Go at the company where I work, and talk a bit about the impact it had, and honorable mentions about software that was written inside the company and used internally, written in Go, of course, and open source contributions of mine that were later then used also in the company to solve aerospace problems. And we'll close off with some insights on where maybe Go fits in the aerospace industry. So let's start out with the team. There we are. First-rate engineers, if I ever saw. I don't know why there's a Jägermeister on the table. I promise we don't usually drink on the job. So, a bit about Leah. Leah is a UK-based company with an engineering department in Argentina. The main focus of this company is to develop propulsion systems for satellites. So, pictured is such a system. It goes on the underside of the satellite, and it would be activated once in space. It doesn't light up before that. Roughly speaking, to give you an idea of what you're looking at there, you got 4 spherical tanks for propellants, so hydrogen peroxide and kerosene, 2 cylindrical tanks for nitrogen, and for all you propulsion buffs, the engine is pressure fed with nitrogen. And the top center, you can hardly make it out, is the flight computer box. There pictured is the liquid bipropellant engine. This is our core technology. So I thought I'd go over how it works. Do we all have a solid base in thermodynamics here? I'm seeing a lot of nods. Wow, okay. I thought I'd recap anyways. So I managed to fit most of it on the slide. Ideal gas laws and you guys know this. Let's just jump ahead. Using ideal gas laws transformations, we can use rocket thrust equation. This is a joke, of course. I'm not qualified to talk about that. He said about to talk about software. That's another thing. Please don't quote me. I'm, as a professional source at least, I don't really know all that much about this stuff. I'm as self-taught as they come. All right, let's get to it. We begin our story before Go arrived at Leah. It's 2020, so year, December, barely 2 months after I joined full-time. We had just failed our first attempt at launching a sounding rocket. Me and a coworker had co-developed a trajectory simulation software in Python to acquire insurance for the launch. So a trajectory simulation software calculates the path of the rocket, sort of in advance of launching it. And for the next launch, so we had failed this one, and the next launch we wanted to modify the program so it was easier to use. And boy, was that hard. I really felt like the language was holding me back. I would tell myself over and over if it was written in Go, it would have been done, long time ago. Frustrated with Python, I wrote an ordinary differential equation solver in Go over Christmas. Before this, I wasn't sure if Go could be used to solve physics problems. Turns out it worked pretty well, better than the Python version. And well, with the successful result, given the successful results, I rewrote the trajectory simulation software in Go from scratch. The rewrite in itself wasn't impactful. It just made an overall pleasure to develop the trajectory simulator. But it did set an important precedent. Go had been used to successfully solve a problem at the company. And that's because this Go program was used to acquire insurance for a second attempt. Fast forward a month, we successfully launched the Zonda sounding rocket. Why did we want to launch a sounding rocket? That's a great question. This is what an end-to-end integration test looks like in the hardware world. It was also a great demonstration of technical capacity. A few companies get this far. In spite of the results, successful results, things could be a lot better. The flight software, so the software that runs inside of rockets, was riddled with mission-critical bugs. It was written by a third party. 2 years on, we're still waiting on the documentation to arrive. The flights, and I kid you not, the flight software build instructions were, here's the SD card, clone it, and figure it out. Yikes. I complain. I might have said something along the lines of, I don't know, I could do this better. To which I was told, can you do it in under a month? The only reason I said yes was because I had been looking at some of the source code for this flight software, and by golly, was it unmaintainable. Spaghetti if I ever saw it. I had no idea if I could do it in under a month, but someone would eventually have to. So there I am, reading datasheet after datasheet for analog to digital converters, WART buses, and other embedded delights. You have to understand, I had zero embedded systems experience. I didn't even know what the term embedded systems meant, and maybe you don't either. Well, think Arduinos. If only I had been given something at this conference that could serve as a demonstration. Maybe you saw this, a buddy gave it to you. It's the TinyGo badge given at the TinyGo Hardware Hack Day. And what you have here is a printed circuit board with a microcontroller on the back and an LCD screen. And it's got buttons and lights which light up. So this is a great example of an embedded system, and you can ask a buddy, maybe that got one. That day there was 99 given out, I think. So, embedded systems. And that's not all of it. The flight software also used an HTTP server to communicate with ground control communication systems. But, and I had a trump card for that. I had developed a forum using Buffalo with a built-in Python interpreter for a free university course, which had handled hundreds of concurrent users. So I thought surely the UI for the flight software would be the easy part, and boy was I wrong. Within 3 days, I had most of the embedded systems peripherals working, such as sensors and actuators. Where did the rest of the month go? The HTTP server. Turns out UI is hard. I've come to think it's the unsolvable side of software engineering. That said, it was working. And surely this rewrite came with some benefits. Some of the benefits were surprises, others not so much. So using Go, the build, oh, that was easy. We went from iterating builds every 2 to 3 weeks with our third-party provider to once every minute, pretty much. And it also went from a fully-fledged mono backend, Angular frontend, SQL server, and God knows what else was running on that thing, to a native binary and HTML templates. Simple. I love it. CPU usage was a huge gain. We went from 60% on all cores to 5% on a single core. And this is huge because remember, this is a flight software. It's running inside of the rocket, and the rocket runs on batteries. Every minute we can get out of it is a valuable minute we get on the pad when the rocket is being prepared. A nice bonus was the code reduction. Down from 6,800 lines of code, overall reduced spaghetti. Not sure if that's due to Go. The quality of life improvements for anyone reading the code. And worth mentioning, the flight software was recently rewritten from 2,800 lines of code to 750 lines of code, and dependencies reduced from 700,000 lines of code to 20,000 lines of code. I tell the higher-ups this is to reduce the surface of failure. I mean, it's true, but honestly, knowing when to rewrite things has paid dividends in maintainability and developer speed and developer happiness. Not to be. And thanks to this latest rewrite, the flight software fits in anyone's head. Newcomers to Leah easily get the hang of it and are easily contribute routines for the critical parts of the software. Today, the flight software is used to test engines. It's seen 18 live fire tests and 90 wet dress rehearsals. A wet dress rehearsal is when we run water through the propellant lines. I'd liken it to a smoke test, if you will. And we've observed some software failures, many hardware failures, but none have been on Go's end. So I guess not speaking on the failures, I guess it's not surprising there was no failures on Go's end, but still, props to the Go team. And here's the rocket engine being powered by Go. Figuratively speaking, of course. And I'm afraid this talk deals with low-stakes problems from now on. At Leah, I am the sole developer of the trajectory simulator. And you might say, wait. What about your coworker who you developed the Python software with? Don't worry about them. They left. I'm sure it had nothing to do with me rewriting all of it in Go behind their back. But had to be done. So, not much to do with this other than simulate planes, satellites, rockets with a state-of-the-art physics model. What is interesting about it is a recurrent experience I've had. On 2 separate occasions, I presented this software to other aerospace company representatives who were developing similarly scoped software for their master's capstone project. This work done for their company was to replace costly commercial software. They both so happen to be using a language I have extensive experience in. I will not mention this language by name, though I will say a friend once aptly described it in one word, the language. Crusty. These people were hitting a wall in development and had to resort to looking for help elsewhere. In this case, Leah. If you ask me today to develop the trajectory simulation in this crusty language, I guarantee I'd lose my mind. Mainly because I know what it's like to have sharp tools, give me a blunt one, and it'd pain me to know that there's something better. In short, I've been spoiled by Go, but also the aerospace industry desperately needs modern languages that help developers. And before anyone asks, this is not play on words. I'm not talking about Rust. And I expect most of you knew that because Rust is a great language. So here we have a 3D visualization of the results of the simulation. This is being shown in a browser using Go, compiled to WebAssembly. Ooh, WebAssembly. Yeah, what'd you think? WebAssembly wasn't mainstream? We're using it at Leah. It's been a while too. So here are some more pictures of this flight simulator in action. You can barely make out a rocket taking that off from our test site in Argentina, though ours didn't make it nearly that high. Just ours was 3 kilometers in height. So, open source stuff, my favorite. I do contribute a lot to open source software, that's OSS. My employer thankfully gives me plenty of liberty in that aspect. And I feel like aerospace software is woefully underrepresented in the OSS world. There's a lot of closed source of it, understandable, and a lot more secretively shared Fortran code. On that, Fortran is the industry standard for aerospace software, and there's no reason for it to be. I mean, it's being taught in university classes for simulation to this day. But oh well, old man yells at cloud. So, an OSS thing I did, a genetic algorithm. So I wrote a machine learning library to optimize vehicle design and orbital maneuvers using the trajectory simulation software I was talking about earlier. What I did to do this was, it might surprise you, I just watched a YouTube video and wrote it kind of like I felt it. We've used it extensively though, and it works great. Other companies have been surprised by our results when I talk to them about. And I'm not going to talk much about it because I am no machine learning expert, and for crying out loud, I wrote the thing basing myself off a YouTube video. So, on an unrelated note, CAD software. Have any of y'all used CAD software? You know, Tinkercad, Fusion 360. I see a few hands. Okay. SolidWorks, all that good stuff. I don't know you guys, but if I had a penny for every time my CAD software threw a topological error, I'd have quite a few pennies. I don't use CAD much in my day-to-day routine, but I do hear the complaints from my coworkers when a surface rounding operation fails. I understand I may be speaking in tongues right now to some of you, or most of you even, but bear with me. So, what we see right there is a plastic 3D printed part. It was generated using the SDFX library, written in Go. It's pipe fitting. We've used it in Leah to control industrial processes. To design these parts, most of the world uses commercially available software with a GUI, graphical user interface. And most of this software uses topological operations to define geometries. There's also this other competing technology called signed distance fields. And why am I making this distinction? Well, signed distance fields don't have many of the limitations that topological defined geometries have. They don't throw errors when you try to do things. They're flexible in that aspect. And in turn, they're much more suited for complex shapes that you might encounter when you want to 3D print something. And why should you care even? Talking about 3D parts, you're all doing distributed systems and stuff. Well, it's my belief that there's an additive manufacturing revolution in the works. 3D printing has become commonplace. I'm sure most of you have heard of 3D printing. And the aerospace industry has normalized metal 3D printing. It's only a matter of time before it finds its ways into other industries and everyday life, and eventually everyday life. So maybe you don't believe me. Well, you're an hour's walk away from a 3D printing a stainless steel gopher. I'm not saying you should, but just think about it, okay? So yeah, it's there. So I think many of you might have thought the talk would deal with this topic. Of course, I'm talking about TinyGo. Hopefully, come this point in talk, I've convinced you that Go does fit in the aerospace industry. It is critical for my company's success, but there is a caveat. If you're going to space, you need microcontrollers to control your system. They're lighter, specialized. They don't run Linux, so they're better for precise timing of some communication protocols you need, or even so, since they don't have Linux, they also use less energy. What I showed you earlier was one had a microcontroller. And since you don't have Linux, no operating system, there's no you can't use Go. Well, luckily, you have TinyGo. I won't talk much about it. Danya's talk is tomorrow, and she'll dive much more in depth about what TinyGo is. I'll just tell you that TinyGo is a Go compiler that allows us Gophers to write Go for our microcontrollers. I think that TinyGo is extremely promising. It's a welcome replacement for aging and industry standard programming language used for aerospace like C and Ada. And I believe as TinyGo becomes more mature, I expect it to be used more in aerospace, and well, it's already been used in other parts of the embedded systems industry. And you might ask, just because you can use Go, should we for microcontrollers? I mean, we got Zig, we got Rust. What's the big deal? So I'd answer with Uh, I don't know for sure, but a voice in my head says yes, 1,000 times yes. So let's summarize a bit about what we talked about today. Go for embedded systems works amazingly well. The resulting code looks and works just like the Go we all love. So, Go is also well suited for complex simulation, at least when compared to the industry standard way of doing things with crusty programming languages. And using Go for visualizing simulation results, also okay. I don't know whether I'd recommend it, but hey, it's better than Java. Okay, let's not. Uh, Nothing is stopping me from using Go to design 3D printed parts and then use them for industrial processes at the company I work. So if you're using plastic, don't use it for high pressure applications, but for water pipes, it works great. That much I can tell you. The absence of topological operation errors is very welcome, but there's still a long way to go in refining these libraries and having a graphical user interface that helps you use SDFs. And finally, TinyGo in aerospace? That's a story for another day. Finally, before I finish the talk, I'd like to mention that we may not be the first company that used Go for aerospace. NASA Jet Propulsion Laboratory has been using Go for embedded systems, I believe. And I also heard Fleet Space is using Go, but I'm not sure. I just heard about this yesterday. I'm not sure what applications they're finding for it. So I got nothing else for you. Thank you.